And we are back. We'll continue the Quarkus topic with a more in-depth look, more advanced look that Stuart, who's working on the project, will tell us about. Stuart, shoot it off.
Okay. My screen sharing going. And so this session is about advanced Quarkus. So first, a bit about myself. My name is Stuart Douglas. I'm one of the founders of the project. I also founded the Undertow project, and I've worked on EAP and Wildfly. Now, I'm going to talk a bit about the topics that I'm going to cover today. So this is a much more advanced look at Quarkus, and it's not really about how to write Quarkus applications, but it more explains how Quarkus works and how to extend Quarkus if you need to, and also a little bit about why you might want to. So there are sort of three main areas. There's the core Quarkus architecture, where we talk about why Quarkus is designed the way it is and what you get out of that. We also talk about how to write extensions, because the extension programming model sort of really shows how Quarkus works. And I think that's the best way to really understand what it is and what it does. And if we have time, depending on how quickly we get through the material, there's also, I'm going to talk about how you can use Quarkus to enable GraalVM and write extensions to help libraries work in native mode. But I'm not sure if we'll get time. We'll see how quickly we get through the material. So what is about Quarkus that makes it so different? So we do a lot of marketing about how Quarkus starts so much faster and how Quarkus uses less memory than other Java applications. And this isn't just marketing. Quarkus has a fundamental different approach than existing technologies such as like Wildfly and Spring Boot. Basically, as much as possible, Quarkus tries to do all its work at build time to keep the actual runtime part of the application as small and fast as possible. So that's a fairly fundamental change in how the deployment and build process actually works. So I don't know if the last presentation had a slide like this, but this is one that a lot of our presentations have done, so you might have seen it before. But this is just a bit of an overview of the Quarkus core architecture. So we have Quarkus core down the bottom here. It's composed of quite a few different pieces. And then all the actual functionality that you use as a user are just separate extensions. Now, because of the way Quarkus works, you can just pick and choose just the bits that you need, so you don't end up with any features that you don't need. And that sort of helps keep things small. But the real advantage is something that this sort of diagram doesn't show, and that is that each of these extensions, and even Quarkus core itself, is actually two different parts. So say the Undertow extension consists of a runtime part and a deployment time part. And each extension, and even the core, has both a runtime part and a core part, and they both do two very different things. So the idea behind this philosophy is that the build time parts basically determine what should happen at startup. So everything that looks at annotations or examines the app to see what services are needed or figures out what order things should start in, these all belong in the build time module. It also includes things like reading build time config or passing XML. So almost anything that we can do at build time, as much as possible, we try and do at build time. And then using that information, we generate the runtime part of the app. Now, the runtime part, we only want to contain classes that are actually needed to run the application. Things that actually serve users' requests, that handle HTTP requests, that sort of thing. And this build and runtime split basically lets us keep the runtime part as small as possible and just let us generate bytecode to directly start the services that are required. Now, when you compare this to a traditional Java application or application server, this makes for a much more efficient sort of startup process. So with a traditional application, with something like Wildfly or EAP or Spring Boot, when the application is starting, it needs to scan the class path for annotations, needs to pass any descriptors or config that might be present. Then it needs to figure out which features are actually enabled and need to be started. Then it needs to generate its own internal meta model to figure out basically what entities map to which tables and all that sort of thing. And then once it's done all that, it can actually start the runtime services that are actually needed to process the requests. Now, Quarkus is a bit different. Once you've generated a Quarkus app, basically all it does at startup is start the runtime services that are needed to process requests. It basically has figured out exactly what it needs already, and it just starts the bits that your application requires. Now, the end result, that means the end result of a Quarkus build should be just enough customized bytecode to start the services that your application requires. Now, that might sound a little bit scary, like you might need to know about Java bytecode to write Quarkus extensions, and you definitely don't. We hide all that away from the developers, and it's something that I'll cover later in my talk. So this has some other benefits as well, and it's not just startup speed. Class loading is one of the slowest things generally when you're dealing with application startup, and like loading classes is quite slow. So by doing all that work at deployment time, it means that there's a lot of classes that you just don't have to load. And because of the way the JVM works, when you load a class, it sits in something called metaspace, and it generally hangs around for the life of the JVM. It is possible to unload classes, but in a lot of cases, especially for this sort of startup type stuff we're talking about, it will be loaded once at startup, and then the JVM will hang onto it for the life of the application. So that means that when you're running an application on the JVM normally, you basically are paying for a big chunk of memory that you only really used at startup that is never going to be used again. It was just a one and done thing. So by moving all that work to build time, it means that we don't actually load those classes into the production application, and that frees up a lot of memory. So as you can see from this comparative graph, which is probably a bit old, I haven't actually updated the numbers to the latest ones, but I assume they're quite similar. So basically Quarkus might use, say, half the memory of a traditional Java application when it's running on the JVM. And then if you compile it down to native, it uses a tiny fraction this is just for a basic REST application. So a lot of the marketing around Quarkus is focused on the native compilation side and how much smaller and faster the native compilation side is. But even if you're on the JVM and are just interested in writing JVM applications, you still get fairly significant startup speed and memory performance improvements. So as an example of one of the things that Quarkus will resolve at build time that would normally be done at runtime is our dependency injection. So with a more traditional system like Wildfly, which uses Weld for CDI and for dependency injection, at startup, it needs to discover all the beans, needs to generate classes dynamically for proxies or for interceptors, needs to use reflection to do a lot of this, and it makes it quite expensive to start. Like dependency injection in Wildfly has been one of the hardest things to optimize to get startup speed and memory usage to be good. And it's been a lot of work over a number of years, and it's still not as good as it could be. Whereas with Quarkus, it uses a specially written dependency injection system called Arc, and it resolves all its injection points at build time. It also generates any proxies or interceptor classes that it needs at build time, and as much as possible just avoids the use of reflection unless there's no other way, like it's a private member. And this results in a much faster startup and much less memory usage, as everything's already been pre-compiled. So it's kind of a lot like Dagger, where Dagger does everything using at compile time. This does everything at application build time. So it's all there, encoded into the app and ready to go. Now, in that last talk, Georgios would have showed off development mode. Now, you might be wondering how development mode is possible when none of that development stuff is present in the application. And the answer is basically that development mode runs in a completely different environment. In developer mode, both the developer, the deployment and runtime parts are present in the same application. And every time something needs to change, the deployment part reruns and effectively generates a new in-memory application. So a production application is optimized for startup speed and memory usage. A developer mode application is just optimized for developer experience. And you won't see anywhere near those same memory gains or startup speed gains, although you should see very fast reloads. So now I'm going to talk a bit about how Quarkus actually does its build time processing and actually show off some code and give you an idea about how it actually works. So everything in a Quarkus extension is run in build step methods. So these are just normal Java methods that are annotated with this build step annotation, which gets processed by our extension annotation processor. And these methods can do one of two things. They can produce and consume what we call build item instances. Now, these are immutable objects, and they're basically just used to pass information between extensions and between Quarkus core and extensions. So this is how extensions communicate with each other, how they read information about the application, and how they generate information that goes into the final application. And we can also record bytecode using recorder objects. Now, these allow you to record specific actions that happen when the application is started. Now, basically, they let you perform normal looking Java invocations at deployment time that don't actually get run at deployment time. They get deferred until the application starts. Now, the best way to show this is with some code. So I'm going to get into a bit of a code example. So, oops. So I'll bring up my IDE. I didn't clean that. And we've got an empty Quarkus extension here. Now, I've prepared this earlier, and I'll actually got a link to it at the end of the presentation. It's on my GitHub, but this is just a hello world extension. So it's got the runtime part and the deployment part that I talked about. And it's also got an application in here, which is not something you would usually have when you're writing an extension. But for the purposes of this demo, it just makes it easier because I can just build the whole thing and show off the extension, what the extension is doing with an application. So that's why I've got an application here with the extension. Now, we have a parent POM, which doesn't really do much except import the Quarkus bill of materials. In the runtime, we depend on a few different extensions. So depending on the runtime part of Quarkus Undertow and Quarkus Jasombe. And we've also got some plugins that extensions need in order to become an extension. So we need this Bootstrap Maven plugin and this extension processor in the compiler. I'm not really going to talk about what they do because this is basically something that you can just copy and paste into any extension that you want to write, and you don't really need to know anything more about it than that. Basically, this is just the bits that actually handle the extension annotations. So in my runtime package, I've got a recorder class, which is just a normal Java class, except that it's got this recorder annotation on it. And I've also got a person class, which we'll use a bit later. In my deployment POM, it's very similar to the other one, except it depends on the dash deployment part of the Undertow and Jasombe extensions. And it also depends on the runtime part of my extension. Now, we also depend on JUnit 5 internal, which is what we use for testing extensions. And I actually have a test here that doesn't really do much. It uses Quarkus unit tests. I don't really have time to talk about how to test extensions, so we might just delete that for now. We can worry about that later. What we do have in the main part is a build step class, which is completely empty at the moment. And I've got an application that just uses my extension. And that's what we're going to use to demonstrate this app. So obviously, the place to start is with Hello World. So we're going to show you the most basic Quarkus Hello World extension. So in my recorder, this is where, because this is the runtime part, this is where the code that actually says hello has to live. So the public void say hello, system.out.println hello world. Now, there's all I need in the recorder. Now, in the build time step, I need to actually invoke this recorder. So I'm going to add a build step. I'm going to say that it uses record, that this build step is going to record bytecode, and that the bytecode is going to be run at static init time. Now, this is something that I might cover a bit later. It doesn't, there's two possible values here, static init and runtime. Generally, you want to run code at static init. It just depends on what you're doing. For a JVM app, it's largely similar. For a native application, static init will only get run once while the application is being built. And runtime code is run every time. So what you're doing will depend on what your extension does, but it's not really that interesting for now. So we're just going to do it in static init. So my build step will be public void hello step. And I need to get access to that recorder, so I'll just inject it here. Hello world recorder. Now I'll do a bit of logging here. System out println about to say hello, and then recorder dot say hello. And there is my basic extension. So now I will fix it. I will build it. A bit bigger. And now that's built. And if we have a look at the Quarkus Maven plugin when it's building our application, which is this bit here, the Quarkus Maven plugin, we can see that as part of that build step process, it says about to say hello. So that build step was executed, but it didn't actually say hello then. So now when I run my application, we can see that's where the actual say hello step happened. So what happens is when you invoke this say hello method, this hello world recorder is actually a proxy that just records the actions that are performed on it. And then it takes those recorded actions and writes that bytecode that will do the same thing at runtime. So this is basically not saying hello now, it's telling Quarkus to say hello at startup time in the future. So we can do, this is a very simple example, we're just calling one method, but we can do more advanced things as well. So we can record a parameter value. So if we want to change who we're saying hello to, say hello name. And then here we can say hello Stuart. And then I might just do this all in one command to save time. So now when we build it this time, we can see that it's actually recorded that parameter name that was passed to it as well. Now, there are some limits on what you can pass, but you can also, there's also a fair bit of flexibility as well. So here I've got a person object, which is a Java bean with getters and setters for the first and last name. But so as well as strings and primitives, we can actually pass Java bean style objects as well. So we can go hello.get first plus and then run that again for the person object. And we'll be able to see that basically as long as Quarkus can figure out how to recreate the object that's being passed into the recorder, it will save the steps that are needed to start to recreate that object at runtime and recreate it before that method is called. So in this case, because this is a Java bean style object with getters and setters, it can figure out that it needs to call that to recreate the state by calling the setters at runtime, and then that object will have the same state. And it can do this recursively as well for like quite complex object hierarchies. It can handle collections and arrays. And one of the things it can also handle is return values from recorders. So let's add a bit of randomness into who we say hello to. So what we might do here is we might create a method here on the recorder that returns a supplier string. And return math.random is larger than 0.5. Stuart, otherwise Elish. So, and then we'll change this recorder method to take a supplier and change who we say hello to. Oops. Now, normally this sort of object, so now what I'll show you is how you can actually use this in the build step. So what we can do here is we go supplier equals recorder dot supplier, and then hello to the supplier, and then we run it and see what happens. So in this case, it said hello to Stuart, but if we run it a few times, we should get a different result. That time it said hello to Alesh. So you can see that that supplier is being used. So you might be wondering how this actually works, because how do we have a supplier here at build time when the supplier doesn't actually exist till runtime? And the answer is that you can't actually use the supplier at build time. If I try and call.get on the supplier at build time before that method is actually called, then you'll get an exception. So basically, you can think of that supplier at build time as a future supplier, or like almost like a promise or a future for something that will exist at runtime. And then when you pass it back into a recorder, Quarkus can use that to figure out that at runtime, the object that gets returned from that supplier call needs to get passed into that hello call, and basically just wire up everything automatically that way. And this doesn't have to happen within the same build step method or even the same extension. So you can create objects in recorders and then use build steps to use build items to sort of communicate them to other extensions. And this allows sort of extensions to communicate and be very flexible in how they communicate using these, basically just using future values that don't actually exist at build time, but are like promises of something to happen. So I think that's basically covers the gist of bytecode recording. It's basically just lets you perform actions at runtime, at build time, that then get executed at runtime. And it means that you don't need to know anything about Java bytecode or think too hard about how objects get represented in the bytecode. You just treat it as normal Java method invocations, and Quarkus takes care of the hard work for you into making sure that that same thing actually happens at runtime when the application actually starts. So now go back to the slides. So recording by itself is interesting, but it's not very useful in a vacuum. Like that extension there really didn't sort of matter what application it was deployed in, it would do the same thing. It doesn't take into account any of the annotations or anything from the application. And so basically recording by itself is not very useful without some way of consuming information about the application and potentially providing other information to other extensions and to Quarkus itself. And the way we do that is via build items. So build items are produced and consumed by these build step methods. So the way you produce them is two ways. You can either just return it from the method itself, or you can inject a build producer as a method parameter and create multiple instances of the build item. Now, to consume them, you just inject them as method parameters. Now, we have two different types of build items. We have simple build item, where there is only ever one of this type of item. Now, these are generally things that you will be consuming rather than producing. So Quarkus Core produces a lot of simple build items that your extension can consume because they provide information about the core of the application. But generally, your extension won't be producing too many of these in most cases. They just consume them. Multi-build item can have any number, and these are generally your extension, if it's producing build items, will be producing a multi-build item, especially if it's integrating with other extensions. So these can be injected just as a... So I've got some examples with some code just to sort of walk through some basic examples, and then I'm going to do another demo just to give a better idea of what you can do. So the absolute simplest build item we have in Quarkus is feature build item. Now, you may have noticed that when Quarkus starts up, it logs the installed features, and that's because this list is driven by a feature build item. So because we didn't produce a feature build item, we didn't get listed in that list. So if I add this build step into our extension, then I can add, by producing this feature build item, it will add my extension name into this list. So very simple example, but not super interesting in a lot of ways. Another interesting one is, well, another more interesting one is additional bean build item. Now, this can be used to turn a class into a CDI bean. So if your extension wants to provide something that other people can inject or wants to be injected itself, you might want to make it into a CDI bean. And because we don't scan the extension contents, we just scan the application, even if your class is annotated with a scope, it won't be picked up. You need to sort of programmatically tell Quarkus that I want this class here to be a bean using this additional bean build item. Another one is servlet build item, which lets you basically register a servlet that will serve web requests. So rather than just returning the servlet build item here, this one injects a build producer. Oops. So rather than returning it, you just call producer.produce and then provide the build item with all the details about the servlet, including the name and the servlet class and the path you want to map it to. And in this case, because we're only producing one servlet, we could have just returned it and it would have done the same thing. But the advantage of build producer is that your build step can produce more than one type of thing, because you can inject lots of build producers, but you can only return one object, and you can return multiple instances of the same thing as well. Like I could use this method to to register multiple servlets if I wanted. Now, another really important build item that almost every extension will use is combined index build item. Now, this basically gives you all the information about annotations and inheritance and which classes implement what interface in the application basically in a pre-generated index that's very efficient and fast to query. So as an example, I've got a little bit of code here. And what this code does is it wants to turn all JAX-RS endpoints into CDI beans. So a JAX-RS endpoint is something that's annotated with this javax.ws.rs.path annotation. So what we do is we look up all the instances of those annotations from the index, and we're iterating over them in a for loop. And then we check to see if that path annotation is on a class. And if it is on a class, we produce an additional bean build item for that particular class. So that just means that everything that is covered is like annotated with this path annotation will get turned into a bean. And as you can see, it's only a couple of lines and it's quite simple. And this sort of thing is very powerful because you can do a lot of annotation processing with just a few lines of code. especially if there are build items and the core functionality already exists and you're just trying to wire up a few things. So you might be wondering about what order these build steps get invoked in. And basically every build step has to produce or record something. So build steps only get run if they're producing something that the build wants to consume. So even if you produce something that nothing else needs, but no other extension wants to consume, then your build step won't get run. So things will only get run if they're actually needed for this particular build. And methods are run in parallel once all dependencies have been produced. So if you're injecting the combined index build item, for instance, your method won't get run until after that's been produced. If you're trying to write an extension that's registering all your servlets and you want to inject all the servlet build items, then it won't be run until everything that can possibly produce a servlet build item has already been run. So basically it just kind of forms a dependent sort of object graph of what needs to run in what order based on the dependencies, and then things are ran as soon as they possibly can be based on all the dependencies being ready. And the generated bytecode runs in this same dependency order that was set up by these build steps. So now that I've sort of given a bit of an introduction to build steps, let's have a look at some code and see what we can actually do with them. So I'll fire up my IDE. Now, what I'm going to do is, rather than having just a static hello world like we had, I'm going to do one where you can use annotations to decide who says hello. So what I'm going to do, I'm going to add an annotation. I'm going to call it, hello. We want retention runtime so you can actually see it. I'm going to add a string value. And that value will determine who we say hello to. So now in my app, I've actually got a few classes in here. I'll add a hello Stuart. So we want to say hello to Stuart. Go to this class and we'll also say hello to Alash. So now we've got two hello annotations. So we want to sort of figure out a way to make our app read those annotations and say hello to both these people. So what I'll do here is I'll get rid of the supplier stuff because we're not going to need that. And I'll just change this to be a string parameter again to keep it nice and simple. And now we'll look at how we change our build step to actually read these annotations. So because it's an annotation, we're going to want to read it from the combined index build item. Now, we're interested in the hello annotation, so we'll grab all that from the index. Annotations equals index.getIndex.get annotations. Now I need to pass in a .name here, which is hello class get name. So that's a little bit more verbose than what it maybe should be. But basically what this is doing is it's looking up every instance of this hello class that's in the application and returning all these as a build time annotation instance, which is a kind of optimized representation of that annotation. So now we just, because it's a collection, we're going to iterate over it. And then with our recorder, we're going to say hello to that person. Just going to say hello, I. Oops, I dot value, because it's a value we want to read, dot as string, because it's a string value. So that should be all we need to say hello to both Alesh and Stuart based on those annotations. So we can see there that it's picked up both those annotations and it said hello to the both of us. Now, let's get a little bit more complicated than that. So far this has just been saying hello on the command line, but I've actually got a web server here and I've got Undertow installed, so we've got servlet. So let's change that so we actually have a hello servlet that can say hello via the web browser. So to do that, we're going to need a servlet. So because a servlet actually handles requests, it needs to go in the runtime module. We'll call it hello servlet. Now, we'll add, oops, we want a list of strings. Names. We need to make a component extend HTTP servlet. Then do get. And then we'll go to rust.getWriter.println. So now this is just a normal HTTP servlet, and it's just using the writer to say hello to everyone. One thing that is different though is that this servlet doesn't have a no argument constructor, and it needs to be created with these names. So this is not something that servlets can usually do. So we're going to have to work around that somehow. So what we're going to do is look at the build step side of it, and then I'll show how we can work around in the recorder. What I'm going to do is I'm going to create a servlet build item. I'm going to create a list of names. Oops. So names, add string. Now I've got our list of names. Now I'll start working my servlet build item. So because we only want one servlet, I can just return it. It uses a builder. We'll call it hello world servlet. The class of the servlet is hello servlet.class.getName. And we'll add a mapping. So we'll map it to /hello. Then we'll build it. But as it is, this isn't going to work because our servlet needs to get access to those names somehow. And because it's being done through a constructor, well, we need sort of some kind of runtime code to construct it. So what we'll do is we'll use a feature of servlet build item called setInstanceFactory. And because the instance factory is responsible for actually creating the servlet, that means it needs to be in runtime. So we'll use our recorder to actually create the instance of this servlet. So we'll go recorder.create servlet, and it's going to need the name, so we'll pass them into it. And now we'll create that method. So now what we need to do is return a new instance factory, which returns a new new instance handle. What's it called? Immediate. Returns a new immediate instance handle. Oops, forgot the new, which is why autocorrect is being weird. Servlet. New hello servlet names. So what we do here in our recorder is we're actually directly creating the servlet from the list of names, and the recorder is returning one of these instance factories that can then be used by the Undertow subsystem. So now, hopefully, if I haven't broken anything, which is unlikely, go. That sort of looks like it's working. And we can see that we're saying hello from our servlet. So basically, this gives an example of how you can write a recorder that creates or returns objects that are used at runtime in one extension. And then you can use a build item here to sort of give that object to another extension and have that other extension use it. So here, our extension is basically instantiated a servlet using some custom code, but then that code actually gets run by the undertow extension as it gets passed to, when the undertow extension consumes this servlet build item. So this basically just gives an idea of how these extensions wire everything together at startup. So if you actually looked at the startup sequence of this app, this would get run to generate the servlet, and that value gets stored somewhere in a map, and then undertow runs and it reads that value and uses it when it sets up its servlet, and it doesn't do much of anything else. So that just hopefully gives you an idea about the sorts of things you can do with Quarkus extensions and how they can communicate with each other, and how Quarkus actually does its build time processing magic to enable applications to start up quickly without needing all the normal scanning code in the actual application. Now, I think I've only got 5 minutes left, so I was planning on talking about native, but I'll just try and rush through it very quickly. Because one of the other things that you can do with Quarkus extensions is you can work around some of the limitations that GraalVM provides. So when you compile a library to native, there are a lot of limitations on things like you can't use reflection unless you sort of specify in advance that you need reflection. You can't use, I'll skip this bit on compile time boot. You can't necessarily generate proxies at build time unless you actually specify. You can't generate proxies unless you actually specify which ones you need. So basically there's a whole heap of information that you need to give GraalVM and Substrate for your application to work properly. And Quarkus basically just provides build items that let you write extensions to do that automatically. So basically one of the ones that this provides is a reflective hierarchy build item. So if you want something to be registered for reflection and want everything it touches to be registered for reflection, so like if you are serializing it to JSON or something, your JSON library you use reflection, then you can just produce a reflective hierarchy build item, and that will tell Graal to register that class for reflection. So here's a very simple example where it looks for everything that implements com.acme.data object and registers the whole thing for reflection. So basically, if you're trying to get a framework or a library or some homegrown code to work on native, the easiest way to do it might be to write a Quarkus extension which can analyze the objects that you know need to use reflection and just register them all automatically. And we provide build items for most of the limitations that Substrate provides. And I think I'm pretty much out of time, so there's about 3 minutes left for questions, if anyone has any. So any questions or?
Looks like everyone's mesmerized by all your examples.
Yeah, there was a bit of content there. I hope it sort of shows just how Quarkus does what it does and moves all the processing, does all the processing at build time, but then still sort of makes it easy to have those same actions run at runtime.
Yeah, there is some complexity under the surface that actually is there to make it possible for you then to use it in a simple way. And Peter Levard has a question. Have you tried Quarkus with Loom?
With Loom?
Fibers?
No. No. Like, I think people have looked into it a bit, but we haven't done any benchmarking or anything like that. Like, we will definitely be looking at that in the future, but at the moment we still support Java 8, so we are going to make sure that everything works well with Loom, but Loom's going to be a big adjustment for a lot of the Java ecosystem, so we'll probably take some time for everything to get there.
And then there's another one, Petar Schell. Let me allow him to talk. Petar, your question? I guess not. Okay, then. I guess this is it. Thanks a lot, Stuart. What's the time at your end?
What was that, sorry?
What's the time at your end?
9:30, so it's not too bad.
Quite far. Okay, thanks a lot. It's been a very interesting lecture, and see you around.
Okay, bye.